Picture this: a silent, solitary spacecraft glides through the vast darkness of Earth's orbit, its mission complete. But instead of drifting aimlessly for decades as just another piece of space junk, it receives a signal, and something extraordinary happens. The craft begins to transform, carefully and deliberately breaking apart into smaller, functional units that either return safely to Earth or reposition themselves for new tasks. This isn't a scene from a science fiction movie. This is the reality of self-disassembling spacecraft, a technological revolution that's unfolding right now above our heads, and it might just be the key to saving our future in space. Consider this staggering fact. There are over 8,000 tons of human-made debris currently orbiting our planet at speeds of up to 17,500 miles per hour. That's equivalent to the weight of more than 500 double-decker buses hurtling through space, each fragment capable of catastrophic damage. This isn't just an abstract problem. It's a ticking time bomb that threatens everything from GPS navigation and weather forecasting to global communications and even human spaceflight. The very infrastructure that modern society depends on is increasingly at risk from this growing cloud of orbital debris, making the development of self-disassembling technology not merely innovative, but absolutely essential for our continued presence in space. In this video, we're going to explore how engineers are turning this visionary concept into reality. We'll dive deep into the fascinating science behind modular spacecraft designs, uncover the revolutionary smart materials that make controlled disassembly possible, and examine the real-world missions that are already testing these technologies today. We'll discover why this capability represents a fundamental shift in how we approach space exploration, one that could transform sustainability, enable more ambitious missions, and even reshape national security strategies. By the end of our journey, you'll understand how learning to take apart what we send into space might be one of the most important steps humanity takes toward preserving the cosmos for generations to come. Imagine a critical communication satellite, a multi-million-dollar asset essential for global connectivity, silently orbiting Earth. Without warning, it is struck by an object no larger than a paint chip. But at a velocity of 17,500 miles per hour, that tiny fragment hits with the force of a grenade, instantly shattering the satellite into thousands of new fragments. Each new piece becomes a projectile itself, capable of destroying other satellites in a cascading chain reaction. This terrifying scenario is known as Kessler syndrome, a potential point of no return where space becomes so littered with debris that certain orbits are rendered unusable for generations. The scale of this problem is almost incomprehensible. Today, space surveillance networks are actively tracking more than 34,000 objects larger than a softball. But that is just the visible tip of the iceberg. Estimates suggest there are over 1 million fragments between 1 and 10 centimeters in size, and a staggering 130 million pieces smaller than that, all moving at speeds faster than a bullet. This creates a hazardous environment where even the smallest particle can compromise a mission or endanger astronauts aboard the International Space Station, which regularly performs maneuvers to avoid potential collisions. This clutter is largely a legacy of how we've traditionally approached spaceflight. For decades, the standard practice was to simply abandon spacecraft and rocket upper stages once their missions were complete. These derelict objects, some the size of school buses, become uncontrolled hazards, lingering in orbit for centuries. They are time capsules of outdated technology, but they are also ticking time bombs, waiting for a chance encounter that could trigger a catastrophic breakup. We have already had chilling previews of this future. In 2009, a defunct Russian Cosmos satellite collided with an operational American Iridium communications satellite. The impact, occurring at an altitude of about 490 miles, created thousands of new pieces of debris, instantly increasing the total trackable objects in low Earth orbit by a significant percentage. This was not a hypothetical event. It was a real-world catastrophe that highlighted the fragile nature of our orbital environment. Near misses are now a weekly, almost daily occurrence, forcing satellite operators to constantly play a high-stakes game of orbital dodgeball. This mounting crisis is the fundamental reason why researchers and engineers are so desperate for innovative solutions. We can no longer afford to treat space as a limitless dumping ground. The need for proactive measures to manage this debris is urgent and universal, compelling the global space community to think differently. This urgency is what leads us directly to one of the most promising approaches on the horizon: designing spacecraft with the built-in ability to disassemble themselves at the end of their lives, transforming a potential problem into a controlled and safe conclusion. Long before engineers drafted the first technical schematics, the concept of a machine that could reshape itself was born in the realm of imagination. Science fiction has always served as a crucial testing ground for future technologies, and self-disassembling spacecraft are no exception. For decades, audiences were captivated by visions of transforming robots and modular starships in films and literature, where vehicles could break apart and reassemble for new purposes. These fictional portrayals did more than just entertain. They planted a powerful seed in the minds of scientists and engineers, challenging them to ask a simple but profound question: if we can imagine it, why can't we build it? This leap from speculative fiction to serious scientific inquiry began to take tangible form in the early 2000s, spearheaded by forward-thinking agencies like DARPA and NASA. One of the most pivotal early programs was DARPA Phoenix Project, officially launched in 2012. Its goal was nothing short of revolutionary: to develop robotic systems that could literally harvest valuable components like antennas from defunct satellites already in geosynchronous orbit. Imagine a robotic mechanic in space, carefully dissecting a retired communication satellite to salvage its still functional parts and attach them to a new, smaller satellite, effectively creating a new spacecraft from the pieces of the old. Phoenix was a radical proof of concept that fundamentally shifted the mindset of the aerospace community, demonstrating that a spacecraft's end of life did not have to be its final chapter. Concurrently, rapid advancements in several key technological fields were converging to make this sci-fi dream increasingly feasible. In materials science, researchers were developing so-called smart materials like shape memory alloys and polymers that could change their properties on command. In the world of computing, the relentless march of miniaturization provided the tiny, powerful processors needed to autonomously manage a complex disassembly sequence. And breakthroughs in artificial intelligence were creating the sophisticated brains capable of making real-time decisions in the unpredictable environment of space. What was once confined to theoretical papers and research grants began to materialize in laboratories around the world as functional prototypes. This momentum was not confined to the United States. Across the Atlantic, the European Space Agency launched its Clean Space Initiative, a comprehensive effort to mitigate the environmental impact of space activities, both in orbit and on Earth. Clean Space became a major champion for design for demise principles, actively funding research into technologies that would ensure future satellites could break apart completely and safely upon re-entry. Meanwhile, major aerospace contractors like Northrop Grumman began investing heavily in related technologies, seeing not just a scientific imperative but a commercial one. Their development of the Mission Extension Vehicle, a spacecraft designed to dock with and rejuvenate aging satellites, is a direct descendant of those early modular concepts, proving that the business case for a sustainable space economy is stronger than ever. The journey of the self-disassembling spacecraft is a perfect example of how human ingenuity works. It shows us that a compelling idea, once born in fiction, can inspire a generation of innovators to spend decades solving the intricate puzzles required to make it real. The visionaries at these institutions didn't just see a way to clean up space. They saw the dawn of a new, more adaptive, and more sustainable era of exploration, built on the foundation of technologies that can change their form and function long after they've left the Earth. Think of a sophisticated children's toy, one designed to transform from a single robot into a fleet of vehicles. This isn't a random explosion of parts, but a precise and choreographed separation along pre-engineered lines. This is the fundamental principle behind self-disassembling spacecraft. They are not built as solid, permanent monoliths. Instead, they are constructed with intentional weaknesses and active release systems that allow for a safe, predictable, and controlled breakup when commanded. The entire process is a masterpiece of reverse engineering, where the end of the mission is as carefully planned as the beginning. At the heart of this technology are ingenious materials and mechanisms that act like the toy's hidden seams and latches. One of the most common is the shape memory alloy. These are special metals that can be programmed to remember a specific shape. A component might be held in place by a pin made of this alloy. When the time comes for disassembly, an electrical current is applied, heating the pin. This heat triggers the alloy to revert to its memorized shape, which might be slightly bent or twisted, thereby retracting and releasing the component it was securing. It's a silent, clean, and incredibly reliable way to initiate separation without any moving parts that could jam. For more forceful separations, engineers turn to pyrotechnic fasteners. These devices might sound dramatic, but they are miniature, highly controlled explosive charges, often no larger than a pencil eraser. When activated, they create a precise burst of energy just powerful enough to shear a bolt or release a clamp. They have been used for decades in spaceflight for one-time events like stage separation on rockets, proving their reliability in the vacuum of space. In the context of disassembly, they provide a guaranteed, instantaneous release for critical connections, ensuring that modules can cleanly break away from one another. Beyond these active mechanisms, the entire philosophy of construction shifts toward modularity. Spacecraft are increasingly being built with standardized mechanical and electrical connectors, much like USB ports for space hardware. These interfaces are designed not only to link components together during the mission, but also to disconnect cleanly when needed. This allows a spacecraft to be conceptually divided into functional blocks: a power module, a communications module, a propulsion bus, and a scientific payload. Each can be individually addressed and separated, turning one large satellite into several smaller, still functional units. Of course, none of this happens by magic. The entire disassembly sequence is orchestrated by a sophisticated onboard computer system, acting as the conductor of this mechanical orchestra. This computer constantly receives data from a network of sensors monitoring everything from structural stress and temperature to the satellite's exact position and orientation. If the system detects an impending failure, or if it receives a pre-authorized command from the ground, it can autonomously execute the disassembly sequence. It will power down specific systems, ensure the spacecraft is in a safe attitude, and then fire the correct release mechanisms in the precise order necessary to avoid any collateral damage. This intelligence ensures that disassembly is a deliberate act of transformation, not a chaotic breakup. We can see these principles in action today in missions that are laying the groundwork for this future. NASA Restore-L project is a brilliant example. It's a robotic spacecraft designed to rendezvous with, grasp, and refuel a satellite that was never meant to be serviced. While its primary goal is refueling, the technologies it's perfecting, precise robotic arms, complex tool interfaces, and machine vision systems, are the exact same capabilities needed to carefully disassemble a satellite, removing valuable components or gently pushing obsolete modules into a disposal trajectory. Similarly, DARPA Robotic Servicing of Geosynchronous Satellites, or RSGS, program aims to develop a free-flying robotic mechanic that could perform intricate repairs and orbital adjustments, demonstrating the fine motor skills required for detailed disassembly work. These programs prove that the foundational technology is not some distant dream. It's being tested and validated in orbit right now, moving us toward a new paradigm where our machines in space are built not for a single life, but for many. For generations, the very skeleton of space exploration has been built from materials chosen for their unwavering strength and permanence. Aluminum alloys, titanium, and carbon composites are incredibly robust, designed to withstand the brutal forces of launch and the unforgiving vacuum of space for decades. But this inherent durability creates a paradox. The same properties that make a satellite reliable during its operational life also condemn it to linger as hazardous debris for centuries after its mission ends. We are now entering an era where this foundational principle is being flipped on its head. The new frontier of spacecraft design isn't about building things to last forever. It's about building things that can end gracefully. This revolution is being powered by a remarkable class of substances known as smart materials, substances that can think for themselves and respond to commands from their environment. These are not your typical metals and plastics. Smart materials possess a seemingly magical ability to change their physical properties, their shape, stiffness, or even their state of matter when exposed to a specific external trigger. It's this dynamic quality that makes them the perfect building blocks for disassembly. Imagine a structural bracket holding two satellite modules together. Instead of being a permanent weld or a stubborn bolt, it's crafted from a shape memory alloy. For the entire mission, it remains solid and rigid, performing its duty flawlessly. But when the spacecraft receives its final command, a small electric current is run through the bracket. The material remembers a different shape it was trained to hold during manufacturing, and it gracefully twists or contracts, unlocking the connection without a single spark or fragment. The separation is silent, clean, and utterly precise. The toolkit of triggers available to engineers is vast and ingenious. For components that don't require such forceful action, there are polymers designed to respond to light. A satellite could be built with panels held together by a special adhesive. At the end of its life, as it tumbles into a specific orientation, it could expose a hidden seam to the intense, unfiltered ultraviolet radiation of the sun. After a calculated period of exposure, the polymer chains in the adhesive break down, causing it to lose its grip and release the panel, allowing it to be safely pushed into a disposal trajectory. For more instantaneous needs, composites can be embedded with microscopic channels filled with a reactive substance. A tiny jolt of electricity can trigger a chemical reaction within these channels that creates just enough gas pressure to fracture the material along a predetermined, clean line. A micro-explosive charge so small and controlled it's more of a precise unzipping than an explosion. Of course, the space environment is the ultimate testing ground. and nothing is approved for flight without surviving a baptism by fire, ice, and radiation in ground-based simulators. These smart materials are subjected to a brutal regimen inside massive vacuum chambers that mimic the void of space, where they are cycled through extreme temperature, swings from 200 degrees Celsius in the sunlight to -200 in the shade. They are bombarded with intense radiation to ensure their molecular structure won't break down prematurely, and shaken violently on shaker tables to simulate the intense vibrations of a rocket launch. The goal is to guarantee that these materials remain perfectly stable and reliable for years, only responding when we specifically want them to, and not a moment before. We are already seeing these concepts move from the laboratory into real missions, particularly in the world of small satellites. Many modern CubeSats, the standardized workhorses of low-cost space access, are now constructed using thermoset polymers and other materials engineered for what's called design for demise. The entire structure is designed to be a consumable. When the time comes for the satellite to deorbit and re-enter Earth's atmosphere, the immense heat of re-entry doesn't just break it apart, it causes the material itself to vaporize completely. The satellite doesn't create debris that might survive to the surface. It transforms into a harmless, incandescent gas, leaving no trace behind. This is the ultimate expression of the philosophy, a spacecraft that literally disappears on command. This fundamental shift in materials science is what turns the concept of disassembly from a neat idea into a practical reality. It provides the physical means to achieve a controlled and safe end-of-life process without resorting to crude, unpredictable methods that could ironically create more problems than they solve. By engineering weakness into our spacecraft in the most intelligent way possible, we are building a stronger, safer, and more sustainable future in space. This material innovation is the silent enabler, the physical key that unlocks the next chapter of our orbital existence. This new way of thinking represents a complete departure from the traditional model of spacecraft design. For decades, we built satellites and probes as singular, monolithic entities. Every component was hardwired, permanently bonded, and uniquely fitted to create one perfect, indivisible machine. It was a masterpiece of integration, but also a finality. If a single critical system failed, the entire multi-million-dollar asset could be rendered useless. The modular design philosophy shatters this old paradigm, reimagining the spacecraft not as a solitary monument, but as a dynamic, reconfigurable collection of interchangeable building blocks. Envision a future spacecraft not as a solid object, but as a cluster of distinct plug-and-play modules. A standardized power unit provides electricity, a dedicated propulsion bus handles maneuvering, and a series of payload slots host various scientific instruments or communication antennas. These modules connect not through custom, one-off wiring harnesses and brackets, but through universal, standardized mechanical and electrical interfaces. Think of it as a cosmic version of the USB standard or a Lego brick connection, but engineered for the brutal extremes of space. This standardization is the absolute bedrock of the entire philosophy. It ensures that a power module from one manufacturer can seamlessly connect to a sensor suite from another, creating an ecosystem of compatible parts rather than a series of isolated, incompatible islands of technology. This approach unlocks a staggering array of benefits that extend far beyond just making disassembly easier. The most immediate advantage is unprecedented mission flexibility and longevity. A communication satellite running low on fuel wouldn't be a lost cause. A servicing vehicle could simply detach its depleted propulsion module and attach a new, fully fueled one, granting the satellite many more years of operational life. A scientific observatory whose imaging technology has become outdated could have its old camera module swapped for a newer, higher-resolution model without needing to launch an entirely new telescope. This transforms space assets from being disposable into being upgradable and maintainable, dramatically increasing their value and reducing the constant need for costly new launches. We already have a magnificent, decades-long proof of concept for this modular philosophy orbiting above us right now, the International Space Station. The ISS is not a single structure. It is a sprawling complex of modules built by different nations at different times using different engineering traditions. Yet they all connect. A Russian Zarya module links to an American Unity node, which in turn hosts Japanese and European laboratories. This has allowed the station to grow, adapt, and evolve over its lifetime. Astronauts regularly perform spacewalks to add new components, replace aging systems, and upgrade scientific gear. The ISS is a living, breathing testament to the power of modularity, demonstrating that this isn't a futuristic fantasy but a practical, proven engineering approach. Furthermore, this design philosophy inherently builds in resilience through redundancy. Instead of having one massive, single point of failure central computer, a modular spacecraft might have several smaller computing units distributed throughout its modules. If one fails, the others can pick up the slack, gracefully degrading performance instead of suffering a catastrophic total failure. This scalability also allows for truly ambitious missions. A single rocket launch could deliver a core module to orbit, and subsequent launches could add more modules, allowing a space telescope or a deep space probe to grow in capability and size over time, funded in stages rather than requiring one colossal, budget-busting project upfront. Ultimately, the modular design philosophy is about more than just convenience. It's about fostering a new, sustainable space infrastructure. It creates the foundation for a circular economy in orbit, where components can be reused, refueled, and repurposed. This drastically reduces the amount of new material we need to launch, and by extension, the amount of waste we leave behind. It shifts our relationship with space from one of consumption and abandonment to one of stewardship and adaptation, ensuring that the incredible machines we send to the heavens are built not for a single purpose, but for a lifetime of service and transformation. Now, let's consider a scenario unfolding in the silent expanse of low Earth orbit. A large, aging satellite, its internal systems degrading after years of reliable service, suddenly detects a critical anomaly. A pressure sensor in its fuel tank reports a rapid, unexplained drop. An onboard artificial intelligence, the craft's digital consciousness, doesn't just register this as a simple fault. In milliseconds, it cross-references this data with readings from temperature sensors, attitude control gyros, and power systems. It runs thousands of simulations against pre-loaded models of spacecraft failure, and its conclusion is grim but certain. An imminent, catastrophic rupture is highly probable. If this happens, the satellite would explode, scattering thousands of pieces of shrapnel into a busy orbital highway. But instead of waiting for commands from a ground control team that might be on the other side of the planet, asleep, the AI makes a decision. It initiates a pre-programmed emergency protocol, commanding the spacecraft to begin a controlled, autonomous disassembly. It safely powers down, vents remaining fuel, and methodically separates its modules along their smart seams, turning one large, dangerous liability into several smaller, manageable pieces that can be safely deorbited or moved to a graveyard orbit. This is the incredible promise of artificial intelligence in space, not just as a tool, but as an intelligent guardian capable of making life or death decisions to protect the orbital environment. This level of autonomous decision-making is only possible because of sophisticated AI algorithms that act as the central nervous system of the spacecraft. These are not simple pre-written scripts. They are complex, adaptive systems designed to process a torrent of real-time data from a network of onboard sensors. They continuously monitor the structural health of the vehicle, listening for the faint acoustic signatures of metal fatigue, tracking microscopic cracks with laser vibrometers, and analyzing thermal patterns that could indicate a looming system failure. The AI's job is to perform a constant, real-time diagnosis, distinguishing between a minor, manageable glitch and a terminal illness that requires immediate end-of-life intervention. It weighs the risks of acting too early, potentially ending a mission that could have continued, against the cataclysmic risk of acting too late. This requires a level of judgment and probabilistic reasoning that was once the sole domain of human engineers on the ground, now compressed into a powerful, radiation-hardened computer brain flying at 17,500 miles per hour. The true magic, however, lies in the predictive power of machine learning. These systems are trained on vast historical datasets of spacecraft failures, simulations, and telemetry from thousands of past missions. By digesting this information, the AI learns to recognize subtle, early warning patterns that would be invisible to the human eye. It might detect that a specific, barely perceptible vibration frequency in a reaction wheel, when combined with a 2-degree temperature rise in a power bus, has a 95% probability of leading to a total failure within 72 hours. This predictive capability transforms the disassembly process from a panicked emergency measure into a carefully choreographed, optimized procedure. The AI can calculate the most efficient sequence for separation, perhaps deciding to jettison a solar array first to create a more stable torque profile before detaching the main bus. It can choose the optimal moment for disassembly, waiting until the spacecraft is in the perfect orbital position to ensure the separated modules enter the safest possible disposal trajectories, minimizing the risk of them ever encountering another object. We can see the precursors to this technology in active development today. The European Space Agency's proposed E.Deorbit mission was designed to use advanced guidance, navigation, and control systems powered by AI to autonomously identify, rendezvous with, and capture a large piece of debris like a derelict satellite. The algorithms needed to safely approach a tumbling, uncooperative object in space are a direct stepping stone to the kind of precision required for a spacecraft to disassemble itself. Similarly, private companies like Astroscale are already demonstrating this technology. Their ELSA D-Servicer satellite uses magnetic capture technology and AI-driven proximity operations to dock with client satellites, a critical capability for future missions where a space tow truck might be summoned to assist with or oversee a disassembly process. These projects are proving that the autonomous intelligence required for this future is not theoretical. It's being coded, tested, and refined in laboratories and in orbit right now. This integration of artificial intelligence fundamentally changes the nature of the technology. It elevates a self-disassembling spacecraft from being a merely reactive machine, following a simple if-then command list, to becoming an intelligent and proactive partner in space sustainability. It possesses situational awareness, foresight, and the ability to make nuanced decisions in the face of uncertainty. This shift is crucial because the time delays in communicating with distant spacecraft and the sheer volume of objects we will have in orbit in the future make human micromanagement impossible. The AI becomes the indispensable pilot, navigator, and physician for its own vessel, entrusted with the profound responsibility of ensuring its death is as safe and orderly as its life. This intelligent autonomy is the key that unlocks a future where our orbital infrastructure can not only operate efficiently, but also retire gracefully, preserving the space environment for the missions and generations that will follow. Imagine the profound impact if this technology became the universal standard for spaceflight. Every year, hundreds of new satellites are launched into orbit. Under the old model, each one of these is a future piece of debris, destined to drift aimlessly for centuries as a collision risk. But if every single new spacecraft were designed from the ground up with self-disassembly capabilities, we could effectively prevent thousands of new debris objects from entering the orbital environment annually. This isn't a marginal improvement, it's a fundamental change to the very life cycle of our space infrastructure, turning a linear model of build-use-abandon into a circular one of build-use-repurpose. The cumulative effect over a decade would be staggering, potentially cutting the projected growth of the debris population by a massive percentage and beginning the long, difficult process of reversing the current trend. The true power of this approach lies in the menu of safe disposal options it provides, each tailored to a specific orbital regime and component type. For satellites in low Earth orbit, controlled disassembly allows for targeted, precise re-entry. Instead of a large, unpredictable object breaking apart violently in the upper atmosphere and potentially raining debris over a wide area, the spacecraft can separate into smaller, more manageable modules. Each module's re-entry path can be calculated to ensure it completely burns up over a remote stretch of ocean, leaving no risk to anyone on the ground. This is the ultimate form of responsible disposal, ensuring that our activities in space don't pose a threat back on Earth. For spacecraft operating in higher orbits, like the critically important geostationary belt 22,000 miles above us, complete re-entry isn't practical. Here, the solution offered by disassembly is a graceful retirement to a so-called graveyard orbit. This is a designated orbital lane a few hundred kilometers above the operational zone. A traditional satellite at the end of its life might not have enough fuel left for this final maneuver, dooming it to drift through active orbital slots. A self-disassembling craft, however, is designed for this moment. Its propulsion module, perhaps the last one to separate, can use its remaining fuel to push the entire stack of inert modules safely up into this celestial junkyard, clearing the valuable geostationary real estate for future missions. This is about being a good neighbor in space, cleaning up after yourself so others can use the shared environment. Perhaps the most forward-thinking benefit is the door it opens to in space recycling and reuse. Why simply dispose of a module when it could be given a second life? A disassembled power unit with perfectly functional solar panels could be collected by a robotic servicer and attached to a new satellite, saving the immense cost and energy required to launch a new one from Earth. This vision of a circular space economy transforms debris from being a problem into a potential resource. While still in its early stages, this concept is supported by international frameworks like the United Nations Guidelines for the Long-Term Sustainability of Outer Space Activities, which explicitly encourage nations and companies to design missions with end-of-life disposal and sustainability in mind, fostering a global shift in mindset. The evidence supporting this proactive approach is compelling. Numerous studies from organizations like the Inter-Agency Space Debris Coordination Committee have run complex simulations showing that merely complying with a 25-year deorbit rule is no longer sufficient to stabilize the debris environment. Their models consistently demonstrate that to actually reduce the number of catastrophic collision risks, we must combine active debris removal missions with widespread adoption of preventive technologies like self-disassembly. When implemented together, these strategies could begin to stabilize the orbital debris population within a few decades, pulling us back from the brink of Kessler syndrome. This research underscores a critical point. Embracing self-disassembly isn't just a nice engineering feature. It's an essential act of preservation. It's about ensuring that the boundless potential of space remains open for business, for scientific discovery, for global communication, and for the dreams of future generations who deserve to inherit a cosmos not shadowed by our neglect. The staggering price tag of reaching orbit has always been the single greatest barrier to a bustling space economy. Building a sophisticated satellite can cost hundreds of millions of dollars. Launching it on a rocket adds another 50 to 100 million, and ensuring the entire endeavor against the high risk of failure, that's a premium that runs into the tens of millions more. For decades, this immense financial outlay was justified by a simple, brutal calculation. The asset was designed for a single, finite life. Once its fuel was spent or a key component failed, the entire multi-hundred-million-dollar investment was simply written off, left to drift as a liability. Self-disassembly technology shatters this unsustainable economic model, transforming space from a graveyard of written-off capital into a dynamic marketplace of reusable assets. The most immediate financial windfall comes from the revolutionary concept of in-orbit servicing and refurbishment. Imagine a scenario where a critical component on a $200 million communication satellite fails, perhaps a star tracker or a power regulator. Today, that failure means the entire satellite is often declared a total loss, a catastrophic financial event for its operators. Now, reimagine that same satellite built with a modular, disassemblable design. Instead of mourning a total loss, the operator simply places a call to an orbital service company. A robotic servicing vehicle, itself a modular craft, launches to rendezvous with the ailing satellite. Using precise robotic arms and standardized tools, it carefully detaches the faulty module and connects a brand new, fresh from the factory replacement. The repair might take hours instead of years and cost $20 million instead of $200 million. This isn't a far-off dream. It's the logical endpoint of the technology being pioneered today. This capability turns a satellite from a disposable consumer product into a maintainable asset, like a high-value piece of industrial machinery or a commercial airliner that is regularly serviced to extend its operational life for decades. This new paradigm is already giving rise to entirely new industries and business models that were previously unimaginable. We are witnessing the birth of the orbital service industry. Companies are now positioning themselves not as satellite manufacturers, but as orbital mechanics and life extension specialists. A brilliant real-world example is Northrop Grumman's Mission Extension Vehicle, or MEV. These pioneering spacecraft are essentially propulsion pods on stilts. They are designed to launch into orbit, rendezvous with an aging but otherwise healthy satellite that is running out of fuel for station keeping, and physically dock with it. The MEV then uses its own thrusters to maintain the satellite's correct orbital position, effectively giving it a new lease on life for many additional years. The client satellite gets to keep generating revenue, and Northrop Grumman collects a service fee that is a fraction of the cost of building and launching a replacement. This model is a direct precursor to the more intricate disassembly and module swapping services of the future, proving there is a massive and viable market for keeping existing assets alive. Looking further ahead, this technology unlocks even more radical economic possibilities, such as in space recycling and manufacturing. Imagine an orbital facility, a kind of cosmic scrapyard and factory combined. Decommissioned satellites that have disassembled themselves into their core modules are towed to this facility. There, robotic systems break them down further. Valuable materials like aluminum, titanium, and even rare metals from electronics could be harvested and fed into large-scale 3D printers. These printers could then manufacture new components, tools, or even entire new satellite structures right there in orbit. The economic implications are profound. Launching raw material from Earth is incredibly expensive, costing thousands of dollars per pound. But if we can source even a fraction of the material for new missions from the skeletons of old ones already in space, we dramatically reduce the cost of construction and our reliance on Earth-bound supply chains. This creates a circular economy in space, turning what was once considered waste into a valuable commodity and foundational resource. This powerful combination of massive cost savings and the creation of lucrative new markets is the primary force accelerating the adoption of self-disassembly technology. While the environmental and safety benefits are compelling, it is the undeniable economic incentive that is truly catalyzing change. Private companies are investing billions because they see a clear path to profitability. Governments are funding research because they understand that sustainable space operations are also fiscally responsible operations. The drive to protect our orbital environment is now perfectly aligned with the drive to maximize return on investment, creating a powerful synergy that ensures this isn't just a scientific curiosity, but the inevitable foundation of the next chapter of our economic expansion into the solar system. In the high-stakes arena of national security, space has become the ultimate high ground, and the ability for a spacecraft to disassemble itself presents a strategic advantage with profound and paradoxical implications. On one hand, this technology offers a powerful defensive capability. Picture a vital military reconnaissance satellite, a billion-dollar eye in the sky, detecting the heat signature of an incoming anti-satellite missile. Instead of sitting idle as a sitting duck, its onboard systems could initiate an emergency disassembly sequence. The main satellite could break apart into several smaller, more maneuverable modules, each darting away on different trajectories, vastly complicating the attacker's targeting solution and increasing the odds of survival. Alternatively, it could release a cloud of decoy modules, each emitting signals that mimic the mothership's signature, creating a bewildering electronic smokescreen that confuses enemy sensors and protects the true asset. This transforms a spacecraft from a vulnerable monolithic target into a resilient, adaptive system capable of active self-preservation, ensuring that critical communication, navigation, and intelligence functions remain online during a conflict. Yet, the very same capability that provides a shield can be forged into a sword with alarming ease. The defensive act of breaking apart can be reinterpreted as an offensive maneuver. A hostile nation could covertly deploy a satellite that outwardly appears peaceful but is, in reality, a dormant weapon. On command, this so-called sleeper satellite could disassemble not into safe, predictable modules, but into a dense, expanding cloud of shrapnel deliberately placed in the orbital path of an adversary's critical assets. This would not be a random collision. It would be a premeditated attack, creating a debris field so dense and hazardous that it could render an entire orbital region unusable, effectively blockading a country from space without firing a single traditional shot. Even more insidiously, a small, stealthy module could separate and maneuver to physically interfere with an enemy satellite, perhaps spraying paint on its optics, jamming its antennas, or even physically grappling with it to induce a fatal spin, all while maintaining a thin veneer of plausible deniability for the aggressor. This dual-use nature has not been lost on the world's military powers, leading to significant investment and a quiet but intense technological race. The United States, through DARPA, is deeply invested in programs that leverage these concepts for strategic resilience. The Blackjack program aims to create a networked constellation of dozens of smaller, more affordable satellites that can operate in a mesh, sharing data and responsibilities. The inherent philosophy of distributed systems aligns perfectly with disassembly technology. If one satellite in the constellation is threatened or damaged, its functions could be automatically transferred to others, or it could break apart to sacrifice a module while preserving the core network. Similar ambitious programs are underway in other nations, with China and Russia also openly developing sophisticated on-orbit servicing and inspection capabilities that straddle the line between maintenance and potential coercion. The goal for every major power is the same: to create a space architecture that is resilient to attack and capable of denying the use of space to adversaries. This rapid militarization underscores a desperate and urgent need for a new framework of international norms and treaties specifically designed for this new era. The existing Outer Space Treaty of 1967 provides a foundational principle that space should be used for peaceful purposes, but its language is often too vague and antiquated to address modern technologies like autonomous disassembly. The world desperately needs clear, verifiable rules of the road that define what constitutes an aggressive act in space. We need agreements that explicitly prohibit the creation of purposeful debris fields as a weapon, that mandate transparency for close proximity operations, and that establish communication hotlines to de-escalate tensions if two nations' satellites have a suspicious encounter. Without these guardrails, a simple misunderstanding or a misinterpreted maneuver could quickly spiral into a catastrophic conflict on Earth, triggered by an incident hundreds of miles overhead. The goal cannot be to prevent nations from protecting their assets. It must be to ensure that the incredible power of self-disassembly is guided firmly toward protective and sustainable applications, preventing a new arms race that could forever contaminate the celestial commons upon which all modern civilization now depends. Perched securely in the payload fairing of its rocket, the Restore-L spacecraft represents one of the most ambitious and practical demonstrations of robotic prowess ever attempted. Its primary target is Landsat 7, a Earth observation satellite that has been dutifully mapping our planet since 1999. Landsat 7 was a marvel of its time, but it was never designed to be touched again after its deployment. It has no grappling fixtures, no standardized ports, and no friendly blinking lights to guide a servicer in. It is, for all intents and purposes, a completely uncooperative target tumbling through space. And that is precisely why NASA chose it. Restore-L is not a mission of convenience. It is a mission of necessity, designed to prove that we can interact with and service the vast majority of existing satellites that were built without any thought for future maintenance. The technological toolkit that Restore-L is pioneering reads like a wish list for the future of orbital disassembly. At the heart of the vehicle is a suite of sophisticated robotic arms, engineered for a level of delicacy and precision that is almost unimaginable. These are not the powerful, rigid arms used to assemble the International Space Station. They are more like the sensitive instruments of a master surgeon, equipped with advanced force feedback sensors. As the arm extends to make contact with the spinning Landsat satellite, it can feel the slightest resistance or unexpected motion and make micro-adjustments in milliseconds to avoid applying a damaging force. This delicate touch is absolutely fundamental because a clumsy attempt to grasp a satellite could send it into an uncontrollable spin or, worse, create a cloud of debris from a shattered solar panel or antenna. Once Restore-L has successfully grappled and stabilized its patient, the real surgery begins. The mission will demonstrate a complex in-space fluid transfer, the cornerstone of refueling. This involves using a specialized tool to cut away layers of thermal insulation, pierce the satellite's fuel valve, and connect a hose to pump in fresh hydrazine propellant. Every single one of these actions, the cutting, the piercing, the connecting, is a direct analog for the kind of manipulations required for disassembly. The same robotic hand that can carefully unscrew a protective cap could just as easily command a module to separate. The tool interface that delivers fuel could be reconfigured to deliver a command signal to a smart material latch. Restore L is, in essence, developing the foundational vocabulary of physical interaction in space, a set of verbs like grasp, cut, connect, and transfer that will be essential for any future mission focused on taking things apart. The lessons flowing from the development of Restore L are already actively shaping the next generation of spacecraft design. Engineers at NASA and its industry partners, like Space Systems Laurel, are now designing new satellites with standardized robotic interface points. They are planning for internal components to be more accessible and considering how fuel lines and power cables can be routed to allow for easier disconnection and reconnection. The mission is proving that for servicing and disassembly to become commonplace, future satellites need to be built not just for their primary mission, but for their entire life cycle, including their eventual retirement and potential repurposing. This shift in design philosophy is perhaps Restore L's most enduring legacy, moving the entire industry toward a more sustainable and flexible approach. This project is also a powerful testament to the collaborative model of modern space exploration. While managed by NASA's Goddard Space Flight Center, Restore L leverages expertise from across the agency and from key commercial partners. This public-private partnership is crucial, as it ensures that the technologies and standards being developed are not just theoretical exercises for a government lab, but are practical, cost-effective, and directly relevant to the emerging commercial satellite servicing industry. The knowledge gained is being shared and integrated, creating a rising tide that lifts all boats and accelerates the entire field toward a future where a mission like Restore L isn't a daring one-off experiment, but a routine service offered by multiple companies. It stands as a brilliant, tangible proof point, demonstrating that the visionary concept of a sustainable, adaptable orbital infrastructure is not a distant dream, but a future we are actively building, one precise robotic movement at a time. While NASA Restore L mission focuses on the intricate art of robotic servicing, the European Space Agency has embarked on a parallel and equally critical path with its Clean Space Initiative, a comprehensive program that tackles the debris problem from a more holistic, cradle-to-grave perspective. The core philosophy of Clean Space is beautifully simple yet profoundly ambitious: to ensure that every new mission launched by ESA and its member states is assessed not just for its scientific or commercial value, but for its entire environmental impact from the manufacturing process on Earth to its final disposal in space. This represents a fundamental shift in mindset, embedding sustainability into the very DNA of spacecraft design from the earliest conceptual stages. It moves the goalposts from simply building brilliant machines to building brilliant machines that are also responsible citizens of the cosmos. One of the most ambitious projects to emerge from this initiative was the groundbreaking E.Deorbit study. This was a mission concept designed to be the ultimate garbage collector, targeting one of the most dangerous classes of debris, a massive, derelict object in low Earth orbit. The plan was as daring as it was necessary: to develop a specialized spacecraft that could autonomously rendezvous with a multi-ton, tumbling piece of debris like an old rocket up a stage or a defunct satellite, capture it using a sophisticated system like a net or a robotic arm, and then act as a celestial tow truck, guiding it on a controlled, final descent to burn up harmlessly in the Earth's atmosphere. While E.Deorbit itself was conceived as an active debris removal mission, the technological challenges it aimed to overcome are the exact same ones that underpin self-disassembly concepts. The advanced guidance, navigation, and control systems needed to safely approach an uncooperative, spinning target are directly transferable to a scenario where a module needs to detach and maneuver away from a main spacecraft. The robust capture mechanisms designed to grapple with a potentially jagged and fragile object inform the design of standardized interfaces for future satellites, ensuring they can be easily grasped and handled, whether by a servicer or for their own controlled separation. Beyond these grand robotic ambitions, clean space has driven remarkable innovation at a much more fundamental level: the very materials spacecraft are made of. A major branch of its research is dedicated to design for demise. This involves a meticulous re-engineering of satellite components to ensure that if they do re-enter the atmosphere, they don't just break apart, they completely vaporize. Engineers are developing and testing new alloys that have lower melting points, experimenting with composite materials that are more susceptible to the extreme heat of re-entry, and even designing internal structures to come apart more predictably under aerodynamic stress. For instance, they might replace a thick aluminum bracket with one made from a thinner, more heat-sensitive alloy, or use plastic components instead of metal screws in non-critical areas. This isn't about building weaker spacecraft. It's about building smarter ones where the choice of material is a deliberate and calculated part of the end-of-life plan. This materials research provides the essential physical toolkit that makes controlled disassembly not just a concept, but a practical reality. The true strength of the Clean Space Initiative, however, lies in its collaborative spirit. The European Space Agency is itself a consortium of 22 member states, and this mission demands a unified effort. The initiative fosters deep collaboration between national space agencies, leading aerospace corporations, and innovative academic institutions across the continent. This collective brain trust pools resources, shares data from testing, and works towards common standards, ensuring that the solutions developed are not just effective for one country, but are scalable and interoperable across all of Europe's future space endeavors. This model of international cooperation is absolutely vital, as space debris is a borderless problem. A piece of junk from one nation's satellite can just as easily destroy another's. By working together, ESA member states are demonstrating that preserving the space environment is a shared responsibility that transcends national interests. This case study powerfully demonstrates that the concept of self-disassembly and proactive debris mitigation is far from a fringe idea or a niche research topic. Through the sustained and well-funded efforts of the Clean Space Initiative, it has been elevated to a central pillar of the European space strategy. It shows a clear-eyed recognition from one of the world's major space powers that the long-term sustainability of our orbital activities is non-negotiable. The technologies being pioneered from the robotic capture systems of deorbit to the demise-friendly materials in their labs are not just theoretical exercises. They are tangible, practical steps being integrated into the blueprints for tomorrow's satellites, ensuring that Europe's future in space is not only ambitious and successful, but also clean and responsible. Now, let's consider a terrifying but plausible scenario. A ground controller sends a carefully verified command to an aging satellite, instructing it to begin its end-of-life disassembly sequence. The command is received, the onboard computer confirms, and the process initiates. But then, something goes horribly wrong. A pyrotechnic fastener, weakened by years of unanticipated radiation exposure, fails to fire with its designed precision. Instead of a clean separation, it creates a jagged fracture, sending a sharp piece of metal spinning away at high velocity. This fragment, in turn, strikes a neighboring module that was moments away from separating cleanly, causing it to break apart unpredictably. In a matter of seconds, a well-intentioned procedure designed to prevent debris has instead created a chaotic cloud of hundreds of new, untrackable fragments, each one a potential bullet threatening other satellites in a busy orbital lane. This nightmare situation is the single greatest engineering challenge facing this revolutionary technology, achieving absolute, fail-safe reliability in the most unforgiving environment known to humanity. The fundamental hurdle is the brutal reality of the space environment itself. Unlike on Earth, where we can perform maintenance and repairs, a spacecraft's disassembly mechanisms must work perfectly the first and only time they are ever called upon, often after decades of silent dormancy. They must remain fully functional while being bombarded by cosmic radiation that can degrade electronics and alter the molecular structure of materials. They have to operate across unimaginable temperature swings, from the searing heat of direct sunlight to the deep, cryogenic cold of shadow, a cycle that repeats every 90 minutes in low Earth orbit, causing materials to expand and contract relentlessly. And they must be hardened against the constant, low probability but high consequence threat of micrometeoroid impacts, which could damage a critical component or mechanism at any moment. Designing a system that can sleep peacefully for 15 years and then awaken to perform a complex, multi-step mechanical ballet without a single error is a monumental task that pushes materials science and engineering to its absolute limits. To conquer these challenges, engineers subject every single component of a disassembly system to a brutal gauntlet of testing that far exceeds the rigors of a standard satellite mission. These mechanisms are placed on massive shaker tables that simulate the violent vibrations of a rocket launch, ensuring they won't accidentally trigger during ascent. They are sealed inside enormous thermal vacuum chambers that replicate the void of space, cycling them through hundreds of extreme temperature transitions to uncover any potential weaknesses. Perhaps most importantly, they undergo accelerated life testing, where they are subjected to years' worth of radiation exposure and thermal cycles in a matter of months. The goal is to force failures in the laboratory that can be analyzed and engineered out of the design long before the hardware ever leaves the ground. This process is expensive, time-consuming, and painstaking, but it is the only way to build the statistical confidence needed to trust a system with the fate of the orbital environment. Given that no test can ever fully replicate a decade in space, the principle of redundancy becomes the ultimate safety net. For any critical release function, engineers design not one, but 2, 3, or even 4 independent ways to achieve it. A module might be held in place by a primary shape memory alloy pin, but also by a secondary pyrotechnic bolt with a backup system that uses a tiny heating element to melt a fusible link. These systems are often designed to be completely independent, with separate power sources, separate wiring, and separate control circuits, so that a single point of failure in one system cannot compromise the others. This layered approach dramatically multiplies the reliability of the entire process. It ensures that if the primary mechanism fails to fire, the onboard computer can immediately diagnose the failure and command the secondary system to take over, still achieving a clean and safe separation. This philosophy of backup upon backup transforms a potentially catastrophic single-point failure into a manageable, albeit unexpected, event. Overcoming these immense technical hurdles is about far more than just engineering pride. It is about building trust on a global scale. For satellite operators, insurance companies, and national regulators to embrace this technology, they must have unshakable confidence that the disassembly system is orders of magnitude more reliable than the risk of doing nothing and leaving a satellite to become derelict. Every successful test, every redundant system, and every validated simulation is a brick in the foundation of that trust. It proves that this is not a reckless gamble with the orbital environment, but a carefully considered, meticulously engineered solution. The ultimate goal is to make controlled disassembly so profoundly reliable that it becomes the unremarkable, standard finale for every spacecraft's mission, seamlessly ensuring that our celestial backyard remains clean and usable for the ambitious explorers and innovators of tomorrow. Navigating the legal framework for space activities today is a bit like trying to use a road atlas from the 1960s to plan a cross-country trip in a self-driving car. The basic roads are there, but the rules for the new technology are completely missing. The cornerstone of international space law remains the 1967 Outer Space Treaty, a monumental document for its time that established space as a province for all humankind, free from national claims of ownership. However, its language is broad and fundamentally silent on the issue of space debris, let alone the specific concept of self-disassembly. It focuses on overarching principles like state liability for damage caused by their space objects and the requirement that nations authorize and continuously supervise the activities of their non-governmental entities. This means if a satellite from one country collides with and damages another's, there's a process for determining fault and liability, but it says nothing about the responsibility to actively clean up after yourself or to design your spacecraft to minimize its long-term impact. This creates a significant gap where the legal focus is on what happens after a disaster occurs, rather than on preventing that disaster in the first place. Recognizing this growing chasm between Cold War-era treaties and 21st century technology, the international community has begun a slow but determined push toward modernization. This effort is primarily channeled through the United Nations Committee on the Peaceful Uses of Outer Space, known as COPUOS. This is where diplomats, lawyers, and technical experts from around the world gather to negotiate the soft law of space guidelines that are not legally binding treaties but carry significant political weight and often form the basis for future national regulations. In 2010, COPUOS endorsed a set of space debris mitigation guidelines, which included recommendations for satellites to be removed from protected orbital regions within 25 years of mission completion. This was a crucial first step, but it's a blunt instrument. It sets a deadline for removal but is completely agnostic about how that removal is achieved, whether through a conventional deorbit burn that requires reserved fuel or through a sophisticated self-disassembly sequence. The committee's more recent guidelines for the long-term sustainability of outer space activities, which began adoption in 2019, go a step further. They explicitly encourage states to consider designing spacecraft for passivation and disposal, and to address risks associated with intentional break-ups. This language gently nudges nations toward the very technologies we've been discussing, creating a global consensus that simply abandoning hardware is no longer acceptable practice. While these international discussions provide crucial direction, the real enforceable rules are increasingly being written at the national level. Every nation that launches objects into space is responsible for licensing and regulating its commercial operators, and many are now weaving debris mitigation directly into those requirements. A powerful example is the United States Federal Aviation Administration, or FAA, which licenses commercial launch and re-entry operations. The FAA now requires applicants to submit a space debris mitigation plan as a condition for obtaining a license. This plan must outline how the operator will safely dispose of their spacecraft at end of life, typically by deorbiting it or moving it to a graveyard orbit. While current regulations don't yet mandate a specific technological solution like self-disassembly, they create a powerful economic and regulatory incentive for companies to adopt the most reliable and cost-effective methods to comply. A startup that can demonstrate its satellite will disassemble and dispose of itself with 100% reliability has a much smoother path through the licensing process than one relying on older, less certain methods. This bottom-up pressure, driven by national regulators, is arguably doing more to accelerate the adoption of new technologies than any international treaty could at this stage. The critical challenge now is to ensure this patchwork of national regulations doesn't become a tangled web of conflicting standards. Imagine if one country mandated a specific type of smart material for separation, while its neighbor required a completely different pyrotechnic system. A satellite designed to meet one set of rules might be illegal to launch from another country, stifling innovation and international cooperation. This is why the current push for global standardization is so vital. Organizations like the International Organization for Standardization, or ISO, are working with space agencies and industry leaders to develop technical standards for interfaces, rendezvous and proximity operations, and even terminology. The goal is to create the orbital equivalent of a universal electrical plug or a standard shipping container, common interfaces that allow satellites, servicers, and recycling stations from different nations and companies to work together seamlessly. Without these universal protocols, the vision of a circular space economy remains a distant dream, trapped by technical incompatibility and bureaucratic red tape. Ultimately, navigating this complex and evolving regulatory landscape is not a side issue. It is just as important as solving the engineering puzzles. Clear, consistent, and internationally harmonized rules provide the certainty that private companies need to invest billions of dollars in developing disassembly and servicing technologies. They give insurance companies the confidence to underwrite these novel missions, and they provide a framework for holding actors accountable if they fail to meet their responsibilities. The law must catch up to the technology, creating a system that doesn't just punish bad behavior after the fact, but actively incentivizes and rewards the good behavior that will preserve the orbital environment for everyone. The success of this entire technological revolution depends on building a legal framework that is as innovative, adaptable, and forward-thinking as the spacecraft it aims to govern. It's completely natural to feel a flicker of unease at the idea of thousands of satellites overhead having the built-in ability to break apart. The very phrase, self-destructing spacecraft, sounds like it was pulled straight from a summer blockbuster, evoking images of catastrophic, fiery failures and a loss of human control over the technology we've sent into the heavens. These concerns are not just valid, they are essential to address head-on if this innovation is to earn the public trust it requires to succeed. After all, space is a shared global commons, and everyone on Earth has a stake in ensuring its safety and sustainability, not just the engineers and corporations developing these systems. The fear isn't that the technology will work as intended, but that it might fail in a way that turns a solution into a significantly larger problem, accidentally transforming a single satellite into a cloud of shrapnel. This leads us directly into a profound and necessary ethical debate. On one hand, we have a powerful moral imperative to clean up our orbital environment and be good stewards of space for future generations. This perspective argues that designing spacecraft to disassemble is an act of responsibility, a way to finally address the legacy of neglect we've created. The alternative, continuing to launch objects designed to become permanent, hazardous debris, could be viewed as the truly unethical path. However, a counter-argument asks a more fundamental question. Is there an inherent wrong in designing something with planned obsolescence, with its own destruction baked into its blueprint. Some might argue it represents a hubristic attempt to control a process that is inherently chaotic, or that it normalizes the idea of objects fragmenting in a domain where fragmentation is the primary source of danger. This ethical tension is at the heart of the issue, forcing us to weigh the potential risks of a new technology against the certain and growing risks of maintaining the status quo. The conversation becomes even more complex when we consider the potential for weaponization, a concern that cannot and should not be dismissed lightly. The same robotic arm designed to gently replace a module could, in theory, be reprogrammed to rip one off an adversary satellite. The same command signal that triggers a safe separation could be hijacked by a malicious actor to cause deliberate, destructive breakups. This dual-use nature is an inescapable reality of many advanced technologies, from nuclear energy to artificial intelligence. The ethical challenge, therefore, is not to pretend the dark potential doesn't exist, but to proactively build a framework of international norms, transparency, and verification that makes hostile applications far more difficult and politically costly than peaceful ones. It's about championing the vision of this technology as a tool for orbital sanitation and sustainability, while openly acknowledging the risks and working relentlessly to mitigate them. This is precisely why transparency and public education are not just optional extras, but critical components of the entire endeavor. Space agencies and private companies cannot develop this technology behind closed doors and then simply announce it as a finished product. To build trust, they must engage in an ongoing dialogue, demystifying the engineering principles and showcasing the immense layers of safety and redundancy involved. Public outreach initiatives, detailed explanatory websites, and open discussions about test results, including failures, are vital. When people understand that a self-destruct command is not a chaotic explosion, but a meticulously choreographed and deeply passive sequence of unbolting and separating, much of the anxiety gives way to fascination. They need to see that these systems are designed to be fail-safe, with multiple independent backups to ensure that if something does go wrong, the default outcome is that nothing happens, not that a breakup occurs. We are already seeing promising steps in this direction. Organizations like the Secure World Foundation and the Space Safety Coalition bring together industry leaders, academics, and policymakers to advocate for sustainable practices and to communicate their importance to a broader audience. Companies like Astroscale regularly publish videos and updates on their debris removal technology tests, making their progress and their challenges visible to all. This open book approach is crucial for transforming public perception from fear of the unknown to informed support for a necessary solution. The ultimate success of self-disassembling spacecraft depends as much on social license as it does on technical brilliance. It requires a collective agreement that this is the right path forward, an agreement built on a foundation of honesty, clear communication, and a shared commitment to protecting the orbital environment that modern life increasingly depends upon. While the ability to safely deconstruct our spacecraft is a monumental leap for orbital sustainability, this technology unlocks a far more profound and exciting future than just cleaning up our mess. It paves the way for a fundamental reimagining of what a spacecraft even is, transforming it from a solitary, rigid machine into a dynamic, living architecture of interconnected parts. The ultimate application moves beyond mere disposal and into the realm of radical adaptability, where a single launch can deploy not one, but an entire fleet of smaller, intelligent units that can work together as a cohesive whole or break apart to perform a multitude of tasks simultaneously. Envision a rocket ascending from its launch pad, its payload not a single large satellite, but a compact cluster of dozens of identical, toaster-sized modules. Once released into orbit, this cluster doesn't just deploy solar panels and begin its mission. Instead, it begins to intelligently disassemble, with each individual unit gently maneuvering away from the central hub using tiny cold gas thrusters. But this is not an end, it is a beginning. These independent modules then use the same autonomous guidance systems that enable safe disposal to instead reassemble themselves into a pre-planned, intricate formation, holding their positions with incredible precision. They are not connected by physical tethers or metal brackets, but by an invisible mesh of wireless data links and inter-satellite laser communications, functioning as one vast, distributed sensor or a gigantic virtual antenna. This is the concept of a reconfigurable swarm constellation, and it shatters every limitation of traditional satellite design. The advantages of this approach are nothing short of revolutionary for practical missions here at Earth. Consider global internet coverage. Instead of relying on a few massive, complex, and incredibly expensive satellites in high orbit, a company could deploy a vast swarm in lower orbits. If one module in the swarm fails, its workload is instantly redistributed to its neighbors, creating a system with built-in redundancy that is virtually immune to single-point failures. There is no catastrophic loss of service, no frantic scrambling to launch a multi-million-dollar replacement. For Earth observation, a swarm could be commanded to reconfigure on the fly. To monitor the progression of a hurricane, the modules could spread out into a wide net, providing a massive, instantaneous snapshot of the entire storm system. The next day, they could collapse into a tight formation to focus their combined sensor power on a specific, flood-ravaged city, providing emergency responders with incredibly high-resolution data. This adaptability means a single swarm could fulfill the roles of a dozen specialized traditional satellites, dramatically increasing the return on every launch. The potential extends far beyond Earth's orbit, into the deep black of interplanetary space. Imagine a large, monolithic spacecraft arriving at Mars after a 9-month journey. Instead of deploying a single, nerve-wracking lander to touch down on the unpredictable Martian surface, the main vehicle could perform a controlled disassembly in orbit. It could release a dozen small, rugged probes, each one independently targeting a different region of interest, one descending into the Valles Marineris Canyon, another landing near the polar ice caps, a third acting as a communication relay in orbit. This would multiply the scientific return of the mission exponentially, providing a diverse set of data points from across the planet for the cost and risk of a single launch. The same principle could be applied to exploring the icy moons of Jupiter and Saturn, where a mothership could release a swarm of tiny melt probes to simultaneously explore the liquid water oceans believed to exist beneath miles of ice, searching for signs of life in multiple locations at once. This is not merely speculative daydreaming. The foundational research is already underway. DARPA SEMI program, which stood for Space-Enabled Effects for Military Envoys, was an early pioneer in this concept, envisioning a constellation of small, disposable satellites that could be rapidly launched to provide troops with on-demand imagery. In academic circles, universities like MIT and Stanford have conducted extensive research into the algorithms and control systems needed for autonomous swarm coordination, running complex simulations of hundreds of satellites working in unison. The technologies being developed for debris mitigation, precise separation mechanisms, autonomous guidance, and standardized interfaces are the exact same building blocks required to make these visionary swarms a practical reality. We are witnessing the convergence of several critical fields of engineering: all pointing toward a future where our presence in space is not defined by large, fragile monuments, but by resilient, adaptable, and intelligent systems that can change their form and function to meet the challenges and opportunities of the final frontier. This vision of a circular economy in space transforms the entire concept of resource management beyond our atmosphere. Instead of viewing a decommissioned satellite as waste to be disposed of, we begin to see it as a valuable source of raw materials, a celestial warehouse of pre-positioned parts just waiting to be repurposed. This shifts the paradigm from a linear model where we launch, use, and discard, to a closed-loop system where materials are continuously used, recovered, and remanufactured, dramatically reducing our reliance on costly launches from Earth and paving the way for truly self-sufficient, long-duration missions to the Moon, Mars, and beyond. The critical enabler of this vision is the rapid advancement of in-space manufacturing technologies. Initiatives like NAS, a Fab Lab concept, imagine a future where orbiting outposts are equipped with multi-purpose fabrication laboratories. These wouldn't be simple workshops with a few spare parts. They would be sophisticated facilities housing advanced 3D printers, robotic assemblers, and material recyclers. Imagine a scenario where a critical bracket on a space station fails. Rather than waiting months for a replacement to be built on Earth and launched on a resupply mission, the crew would simply feed a broken component from a disassembled satellite into a recycler. The machine would melt down the old metal, purify it, and then feed the raw material into a 3D printer, which would fabricate a brand new, perfectly designed bracket within hours. This isn't science fiction. It's the logical endpoint of technologies being proven today. Pioneering companies are already laying the groundwork for this industrial revolution in orbit. Made in Space, now a part of Redwire Space, made history by installing the first commercial 3D printer on the International Space Station back in 2014. Their experiments have successfully demonstrated that functional tools, medical supplies, and even complex components can be manufactured on demand in microgravity. The implications are profound. A printer cartridge filled with polymer feedstock is vastly lighter, smaller, and cheaper to launch than an entire pre-made toolkit for every conceivable repair. This proves that launching the factory is smarter than launching the warehouse, and that the most efficient way to supply a deep space mission is to send the means of production, not just the products. The missing link in this chain has always been a reliable source of raw material. This is where the synergy with self-disassembling spacecraft becomes absolutely transformative. Disassembly provides the necessary feedstock. A retired communication satellite becomes less of a debris hazard and more of a mineral deposit in space, rich with aerospace-grade aluminum alloys, titanium, copper wiring, and even silicon from its solar panels. Robotic services, perhaps descendants of missions like Restore-L, wouldn't just deorbit these old craft, they would carefully dissect them, sorting valuable materials into different streams. These sorted materials would then be transported to orbital recycling facilities where they would be processed, melted, purified, and reformed into standardized wire or powder feedstock, ready to be fed into the hungry 3D printers that will build the next generation of satellites and space habitats. We already have compelling proof-of-concept experiments demonstrating the feasibility of this closed loop. Aboard the International Space Station, astronauts have conducted tests with the Refabricator, a device that is both a recycler and a 3D printer. It can take a plastic item that has outlived its usefulness, melt it down, and use that same material to print a new, useful object. Another experiment, the Made in Space Recycler, studied how different plastics behave when melted and recycled in microgravity, providing crucial data for designing larger-scale systems for metals and other materials. These experiments are the humble, early steps toward a future where a mission to Mars could manufacture and repair its own equipment using components from its landing craft, or even utilize Martian regolith, turning the very dust of the planet into building blocks for a sustained presence. This powerful integration of disassembly and manufacturing doesn't just solve the debris problem. It fundamentally rewrites the economics and logistics of space exploration, enabling a future where humanity is not just a visitor to space, but a permanent, growing, and sustainable resident. The same revolutionary principles that allow a satellite to gracefully disassemble in orbit are already beginning to transform industries right here on Earth, creating a powerful ripple effect that turns space-age innovation into everyday convenience. This cross-pollination of technology is a classic story of ambitious challenges begetting universal solutions. The extreme demands of the space environment, where failure is not an option, and every gram must serve a purpose, force engineers to create systems that are incredibly efficient, intelligent, and resilient. Once perfected for space, these breakthroughs inevitably find their way back to terrestrial applications, solving old problems with radical new approaches and driving progress in fields we interact with every single day. Consider the challenge of construction and demolition, an industry historically known for its waste and disruption. The smart materials being developed for spacecraft polymers that degrade with specific light exposure or alloys that change shape with a jolt of electricity could revolutionize how we deconstruct buildings. Imagine a future high-rise designed for its entire life cycle. At the end of its useful existence, instead of bringing in noisy, diesel-powered excavators and wrecking balls that create clouds of dust and mountains of mixed debris, crews would simply activate a carefully planned sequence. Key structural supports fabricated with materials sensitive to a particular electromagnetic signal would gracefully lose their integrity. Walls and panels, held together by adhesives designed to break down when heated to a precise temperature, would cleanly separate. The result wouldn't be a chaotic pile of rubble, but a neat sorting of components. Concrete here, steel beams there, glass panels over there, all pre-sorted for highly efficient recycling. This would drastically reduce the 30% of landfill waste currently attributed to construction and demolition, turning a messy end into a clean and valuable new beginning. The consumer electronics sector, notorious for its rapid cycle of obsolescence and massive electronic waste problem, is another prime candidate for a space-inspired overhaul. The modular design philosophy at the heart of self-disassembling satellites is a direct answer to the frustration of a cracked smartphone screen or a failing laptop battery, rendering an entire device useless. Companies like Framework Computers are already pioneering this approach with laptops designed like Lego sets, where every component from the keyboard to the mainboard is user-replaceable with standard screws. This philosophy could be supercharged with space-grade innovations. Circuit boards could be printed with conductive inks that lose their adhesion when exposed to a specific frequency of sound, allowing them to be literally shaken apart to recover precious metals like gold and copper. Batteries could be housed in smart casings that, at the end of their life, automatically initiate a safe chemical neutralization process, preventing the toxic leaks that plague traditional e-waste recycling. This shift from monolithic, glued-shut devices to modular, repairable, and easily separable products wouldn't just be convenient for consumers. It would fundamentally dismantle the throwaway culture and create a circular economy for our gadgets. Perhaps the most profound impact will be felt in the maintenance of our critical infrastructure, from bridges and power grids to pipelines and wind turbines. The autonomous artificial intelligence systems that allow a spacecraft to diagnose its own ailments and execute a complex disassembly sequence are directly applicable to predicting and preventing catastrophic failures here on Earth. Networks of sensors embedded in a bridge's structure, much like those on a satellite's frame, could continuously monitor for microscopic cracks and metal fatigue. An AI trained on vast datasets of structural failures could analyze this real-time data, not just to sound an alarm when a problem is imminent, but to predict it months or even years in advance. It could then automatically schedule and even guide robotic repair drones to the exact location to perform precision welding or reinforcement, all without ever requiring a human to put themselves in harm's way for a dangerous inspection. This transition from reactive repair to predictive, autonomous maintenance, a direct descendant of satellite autonomy, would make our essential infrastructure infinitely safer, more reliable, and more cost-effective to manage. This flow of innovation is not a happy accident. It is the result of intentional and growing collaboration between the aerospace industry and nearly every other sector of the economy. Automotive companies are partnering with space agencies to develop new lightweight composites and autonomous driving systems derived from planetary rover technology. Medical device manufacturers are adapting miniature spectroscopic sensors used to analyze the chemical composition of distant asteroids into handheld scanners that can identify tissue abnormalities or diagnose infections non-invasively. Even the agricultural industry is benefiting, using satellite-based autonomous navigation and monitoring systems to enable precision farming, where water and fertilizers are applied with pinpoint accuracy to individual plants, boosting yields while conserving resources. This widespread cross-pollination demonstrates that the billions invested in space technology are not spent in a vacuum. They represent a powerful down payment on a wave of innovation that washes over the entire economy, creating smarter products, more efficient industries, and a higher quality of life for everyone. The quest to sustainably manage our presence in space is quite literally helping us build a better world down here on Earth. What we are witnessing now is nothing short of a global technological sprint. A high-stakes race where national prestige, economic dominance, and the very future of space access are all on the line. This isn't a quiet research project confined to a few laboratories. It is a vibrant, competitive, and sometimes contentious arena where the world's superpowers and a new wave of ambitious private companies are all vying for leadership in the burgeoning field of space sustainability and disassembly technology. Each player brings a distinct strategy and set of resources to the table, creating a dynamic landscape that is simultaneously driving breathtaking innovation and presenting new challenges for international cooperation. The United States has powerfully leveraged its tradition of public-private partnership to foster a thriving commercial ecosystem. Through agencies like NASA and the Space Force, the government acts as an anchor tenant and a source of lucrative contracts, funding the development of critical technologies through programs like the Restore-L servicing mission and the Orbital Prime initiative for debris removal. This strategy has catalyzed a boom in American startups like Astroscale, which is demonstrating active debris capture, and NanoRacks, now part of Voyager Space, which is pioneering concepts for in-space manufacturing and recycling. They are joined by aerospace titans like Northrop Grumman, which has already successfully deployed its mission extension vehicles to give aging satellites new life, proving there is a viable market for these services. This model creates a powerful innovation engine where competitive private companies drive down costs and accelerate development, all while serving national interests in securing the space domain. Meanwhile, China is pursuing a rapid and state-driven approach that reflects its long-term strategic ambitions. With the full backing and funding of its national space program, China has made remarkable strides in space robotics and rendezvous technology. Its series of secretive Xi'an satellites have performed complex on-orbit maneuvers, including demonstrations of robotic arms that could easily be adapted for both servicing and disassembly tasks. The country's ambitious Chang'e space station serves as a perfect testbed for these technologies, with its own robotic arm capable of precision movements. China's strategy is one of centralized control and long-term planning, viewing dominance in space infrastructure and sustainability not just as an economic goal, but as a cornerstone of its geopolitical power. This fundamentally different approach creates a parallel track of development, one where progress is swift but often less transparent, raising questions and concerns among other spacefaring nations about the ultimate intentions behind these advanced capabilities. Caught between these two very different models is Europe, which has chosen a path defined by collaboration and consensus. Through the European Space Agency and its Clean Space Initiative, member states pool their resources and expertise to tackle the debris problem. This collaborative model avoids duplication of effort and allows for the undertaking of large-scale, high-risk projects that might be too costly for any single nation, such as the proposed Clear Space 1 debris removal mission. The strength of the European approach lies in its commitment to establishing norms and best practices that are adopted across its many member states, creating a large bloc of countries aligned on sustainability principles. However, the downside can sometimes be a slower, more bureaucratic process of decision-making compared to the agile private companies in the US or the singular focus of China's state-led program. This makes Europe a crucial diplomatic force and a leader in setting standards, even if it sometimes cedes the headline-grabbing, rapid-fire demonstrations to other players. And then there are the private enablers, companies like SpaceX, whose actions indirectly make the case for disassembly more urgent than ever. By driving down launch costs with reusable rockets and deploying mega constellations of thousands of Starlink satellites, SpaceX has fundamentally altered the economics and the physical reality of low Earth orbit. On one hand, this proliferation of satellites dramatically increases the urgency of solving the debris problem. A single collision in a densely populated orbital shell could be catastrophic. On the other hand, the company's success proves the viability of a large-scale, distributed architecture in space, which is the very same model that future disassembly and servicing infrastructures will rely upon. Other companies like the US-based Orbit Fab are aiming to become the gas stations of space, developing standardized ports for refueling, a technology that is a close cousin to the interfaces needed for modular disassembly. This intense private sector activity ensures that the push for these technologies is being driven by market forces and a clear commercial imperative, not just government mandates. This multifaceted global race is a powerful catalyst for innovation, as competition pushes every player to move faster and think bigger. However, it also carries a significant risk: fragmentation. If the United States, China, Europe, and various private entities all develop their own proprietary technologies, interfaces, and communication protocols, we could end up with a celestial Tower of Babel. A satellite built with American docking ports might be completely incompatible with a European servicing vehicle, while a robotic arm designed for one country's satellites might be unable to grapple with those from another. This would defeat the entire purpose of a sustainable ecosystem, creating parallel and incompatible systems that could actually increase the complexity and danger in orbit. Recognizing this peril, there are growing efforts to foster cooperation amidst the competition. Initiatives like the World Economic Forum's Space Sustainability Rating are a brilliant example of this. This system acts like a LEED certification for satellites, assigning a rating to missions based on how sustainably they are designed and operated, with points awarded for features like clear disposal plans, use of standardized interfaces, and design for disassembly principles. While voluntary, such a rating creates a powerful incentive for all players, governments, and companies alike to adopt greener, more compatible practices, as a high rating could become a prerequisite for insurance, licensing, and international collaboration. This kind of soft power diplomacy, focused on creating shared standards and transparent goals, may be our best hope for ensuring that the global race to lead doesn't end in a chaotic and dangerous deadlock, but rather propels all of humanity toward a cleaner and safer future in space. This technological revolution isn't just happening in government labs and corporate boardrooms. It's taking root in university classrooms and student workshops around the globe, fundamentally reshaping how we educate the engineers and innovators of tomorrow. The traditional aerospace curriculum, once dominated by rigid structures and siloed specializations, is being completely reimagined to embrace the new paradigm of adaptability, sustainability, and systems thinking. You can now walk into engineering departments where students aren't just learning about orbital mechanics. They're actively designing and building functional modular satellites, known as CubeSats, that incorporate basic disassembly principles right from the start. These aren't abstract exercises. They are hands-on projects where teams must grapple with the same real-world challenges facing major agencies: how to create secure but releasable connections, how to manage power distribution across separable units, and how to write software that can autonomously manage a safe separation sequence. This practical, problem-based learning is producing a new breed of engineer who thinks in terms of entire life cycles, not just mission durations. The skill set required for this new space economy is vastly more interdisciplinary than ever before. It's no longer enough to be a brilliant mechanical engineer or a specialist in propulsion. The next generation needs to be fluent in the language of materials science, understanding how smart alloys and polymers behave over decades in the harsh space environment. They need a deep grounding in robotics and artificial intelligence to design the autonomous systems that will manage complex disassembly and servicing maneuvers. They must be systems engineers who can see the big picture, understanding how a change in the power module affects the thermal management of a payload and the software that controls it all. This requires a fundamental shift in education, breaking down the walls between classical engineering disciplines and creating collaborative learning environments that mirror the integrated teams students will join in their professional careers. This shift is powerfully embodied in international student competitions, which have become crucibles for innovation and talent development. Events like the European Rover Challenge or the NASA-sponsored robotic mining competition are no longer just about building a better robot. They are complex simulations of real-world space scenarios. At the European Rover Challenge, student teams from across the world must design rovers that can not only navigate harsh terrain, but also perform intricate tasks like manipulating objects and conducting repairs with a robotic arm, a direct analog for the in-orbit servicing work of the future. These competitions force students to think about reliability, redundancy, and graceful failure modes, all essential concepts for a spacecraft that might need to take itself apart. The pressure is intense, the deadlines are real, and the experience is arguably as valuable as any single semester of lectures, producing graduates who are not just theoretically knowledgeable but practically capable and ready to contribute from day one. Recognizing this urgent need for a new talent pipeline, major space agencies and private companies are proactively investing in these future innovators through targeted programs and internships. NASA CubeSat Launch Initiative provides universities with opportunities to fly their student-built satellites, giving them invaluable real-world experience in mission design, integration, and operations. The European Space Agency's Academy offers extensive training programs and hands-on campaigns, like the Fly Your Thesis program, where student experiments are tested on parabolic flights experiencing microgravity. Perhaps even more impactful are the direct partnerships between industry and academia. Companies like Astroscale, SpaceX, and Lockheed Martin are establishing dedicated internship programs focused specifically on space sustainability, offering students the chance to work alongside leading experts on actual flight hardware and software. These experiences are invaluable, transforming abstract classroom concepts into tangible skills and professional connections that launch careers. This concerted effort is fueling the rapid growth of entirely new career paths and job markets. A decade ago, a job listing for a space debris mitigation engineer or an in-orbit servicing systems architect would have been unheard of. Today, they are becoming increasingly common. The demand for specialists who can design for disassembly, develop autonomous rendezvous and proximity operations software, and create business models for orbital recycling is skyrocketing. Universities are responding by launching dedicated master's programs and research centers focused on space sustainability, ensuring a steady stream of qualified graduates ready to fill these roles. This isn't a niche field, it is becoming a central pillar of the global space industry, creating a virtuous cycle where educational investment creates a skilled workforce, which in turn drives further technological innovation and economic growth. The success of this entire technological shift ultimately depends on the minds we nurture today, making the classroom and the university lab just as critical to our future in space as the launch pad and the mission control center. The financial engines powering this new space age are roaring to life, and a significant portion of that capital is now being steered directly toward the crucial mission of sustainability. We are witnessing an unprecedented surge in investment, a powerful vote of confidence from both venture capital titans and government treasuries, all betting that the technology to clean up and maintain space will be one of the most lucrative and essential markets of the coming decades. This isn't a trickle of funding, it's a flood channeling billions of dollars into startups and established companies that are transforming the visionary concepts of disassembly and servicing from whiteboard schematics into flight-ready hardware. The message from the market is clear. A sustainable space economy is not just an environmental imperative, it is a phenomenal business opportunity. This investor enthusiasm is vividly illustrated by a series of major funding rounds for pioneering companies. Orbit Fab, a company with the ambitious goal of becoming the gas stations of space, has successfully raised tens of millions of dollars from venture firms. Their focus on developing standardized refueling ports and shuttle tankers is a foundational piece of the puzzle. A spacecraft that can be refueled is a spacecraft whose life can be extended, making eventual disassembly a choice rather than a necessity. Similarly, the Italian company D-Orbit has secured significant investment for its innovative orbital transfer vehicles and its dedicated debris removal services, which rely on capture and disposal technologies that are direct cousins to disassembly systems. These companies and dozens of others like them are proving to investors that there is a real, addressable market with paying customers, satellite operators, who are desperate for solutions that protect their multi-million-dollar assets and ensure regulatory compliance. The calculus for these investors is remarkably straightforward and goes far beyond altruism. They recognize a perfect storm of market forces converging. Firstly, there is the exploding demand for debris-free orbits. The proliferation of mega-constellations like Starlink and OneWeb has created incredibly dense and valuable orbital highways. A single collision in one of these lanes could trigger a chain reaction that wipes out billions of dollars in infrastructure. Satellite operators, therefore, have a massive financial incentive to ensure their own satellites are responsibly managed and to support services that remove any potential threats nearby. This creates a powerful, built-in customer base for disassembly and servicing technologies. Secondly, the regulatory environment is rapidly tightening. With national agencies like the FAA requiring concrete debris mitigation plans for licensing, companies that can offer guaranteed, cost-effective disposal solutions suddenly have a tremendous advantage. Investors see a future where these services aren't optional extras, but mandatory parts of doing business in space, creating a predictable and growing revenue stream. Crucially, this private sector dynamism is being powerfully amplified by targeted government grants and support programs. In the United States, NAS, a small business innovation research program known as SBIR, has been a vital lifeline for countless startups. Through SBIR, small companies can receive non-dilutive funding to develop and mature high-risk, high-reward technologies that align with national space goals, including on-orbit servicing and debris mitigation. Across the Atlantic, the European Space Agency's business incubation centers provide a similar function, offering seed funding, technical expertise, and business development support to entrepreneurs turning space sustainability ideas into viable companies. This symbiotic relationship is incredibly effective. Government funding de-risks the early-stage technology development, giving private venture capital the confidence to swoop in with larger investments for scaling up and commercialization. This public-private partnership is the rocket fuel accelerating the entire industry, ensuring that brilliant ideas don't languish in the lab but are propelled toward the launch pad. Even the most brilliantly conceived technology carries with it a shadow of potential unintended consequences, and the ability to command a spacecraft to take itself apart is no exception. While designed as a solution to the debris crisis, we must confront the sobering reality that if these systems fail or are misused, they could ironically become a primary source of the very problem they were built to solve. The nightmare scenario for any engineer in this field isn't a system that refuses to work, but one that works incorrectly at the worst possible moment. Imagine a critical separation command is issued, but due to a tiny manufacturing defect in a single pyrotechnic bolt or a software glitch in the timing sequence, a module doesn't separate cleanly. Instead, it fractures, shattering into a cloud of sharp, high-velocity fragments. This wouldn't be a controlled disassembly. It would be a catastrophic breakup, instantly creating hundreds of new debris objects in a matter of seconds. Each one of those fragments then becomes a potential weapon, capable of triggering a chain reaction of collisions in a densely populated orbital lane, turning a well-intentioned end-of-life procedure into the catalyst for a regional disaster. Beyond the specter of accidental failure lurks the even more sinister threat of deliberate malicious action. In an era where state and non-state actors are constantly probing for vulnerabilities in critical infrastructure, a spacecraft equipped with a self-destruct command presents a tantalizing target for cyber warfare. The entire concept relies on a secure communication link between the ground and the satellite. If a hostile entity were to successfully hack that link, they could potentially spoof a disassembly command, triggering a spacecraft to tear itself apart prematurely. The motivations for such an attack could be vast: to disrupt a rival nation's military reconnaissance or communication capabilities, to sabotage a commercial competitor's asset, or simply to create chaos and demonstrate technological prowess. The result would be the same: the intentional creation of a debris cloud as an act of war or terrorism, holding the orbital environment hostage. This underscores that the security of these systems isn't just an IT concern. It is a foundational requirement for global space security, demanding military-grade encryption, robust authentication protocols, and perhaps even autonomous systems that can recognize and reject commands that don't align with pre-programmed safety parameters. We must also cast our gaze further into the future to consider the long-term, systemic consequences of widespread adoption. If every new satellite is designed to disassemble and move to a graveyard orbit at the end of its life, we risk solving one problem by creating another. These graveyard orbits, located a few hundred kilometers above the most valuable operational zones, could themselves become dangerously overcrowded over the course of decades. While the objects there are not an immediate collision threat to active satellites, they are not gone. They represent a massive amount of mass parked in an unstable equilibrium. A collision within a graveyard orbit, while statistically less likely, would be catastrophic, generating a debris field that could eventually drift down into operational altitudes. Furthermore, for satellites in low Earth orbit designed for complete re-entry, the process of disassembly must be meticulously managed to ensure no surviving fragments reach the ground. A miscalculation in the trajectory of a dense, heat-resistant component like a reaction wheel or an optical mirror could mean that instead of safely burning up, it survives re-entry and impacts a populated area. The liability and ethical implications of such an event would be immense, potentially halting the entire industry in its tracks. Confronting these daunting risks is not a reason to abandon the technology, but rather the most powerful argument for developing it with an unwavering commitment to safety and redundancy from the very beginning. The engineering philosophy must be one of designing for failure. This means building in multiple, independent layers of protection. Every critical release mechanism should have a backup, and that backup should have a secondary backup, each with its own separate power source and control circuit to prevent a single point of failure from dooming the entire process. Cybersecurity cannot be an afterthought. It must be baked into the hardware and software at the most fundamental level, with continuous monitoring for anomalous signals and the ability for the spacecraft itself to enter a safe mode if it detects a potential intrusion. Finally, this cannot be a solitary endeavor pursued by individual nations or companies. It demands unprecedented international cooperation in the form of shared monitoring networks. A global space traffic management system where all nations contribute data and adhere to common protocols for end-of-life operations is essential for tracking every object, predicting potential conjunctions, and maintaining the long-term stability of both operational and graveyard orbits. By openly acknowledging these risks and proactively building the systems to mitigate them, we can ensure that this powerful technology fulfills its destiny as a tool for preservation, not destruction. Right now, the burgeoning field of spacecraft disassembly is facing a critical bottleneck that has little to do with engineering prowess and everything to do with coordination. Imagine if every smartphone manufacturer used a different proprietary charging port. You couldn't borrow a friend's charger in a pinch, and companies would waste resources reinventing the same basic technology. This is precisely the situation we're barreling towards in orbit. There are currently no universally accepted standards for how a servicing vehicle should physically connect to a client satellite, what commands it should use to initiate a disassembly sequence, or even how different modules should communicate their status and intent. A robotic arm designed by a company in the United States might be completely unable to grapple with a satellite built by a European consortium, not because of a lack of capability, but because the two entities designed their interface fixtures without any consultation. This lack of common language and common hardware threatens to create a celestial Tower of Babel, where a future filled with interoperable, sustainable space systems is hamstrung by simple incompatibility. This critical challenge of standardization is why organizations like the International Organization for Standardization, known as the ISO, are now stepping into the vacuum. The ISO is a globally recognized body that develops and publishes voluntary international standards for everything from the thread pitch on a screw to the protocols for data security. Their work is foundational to modern global trade and technology, ensuring that products from different parts of the world can work together seamlessly. The ISO has established a dedicated technical committee for space systems and operations, which is actively working on crafting standards for on-orbit servicing, including the interfaces and processes critical for disassembly. Their goal is to create a set of detailed, consensus-driven technical specifications that manufacturers around the world can adopt, ensuring that a satellite launched from Japan has the same basic docking port and communication protocol as a servicing vehicle launched from Brazil. This isn't about stifling innovation or creating a one-size-fits-all mandate. It's about creating a common playing field upon which everyone can innovate more effectively. Alongside these formal standards bodies, industry-led coalitions are also playing a vital role in driving consensus from the ground up. The Space Safety Coalition is a prime example, a group of leading satellite operators, manufacturers, and insurers who have come together to promote best practices for space safety and sustainability. While they don't create technical standards in the same way as the ISO, they wield immense influence by publishing recommended guidelines and best practices. Their work helps to create market pressure for standardization. A satellite operator may find it easier to secure favorable insurance rates or attract partners if their spacecraft are built to comply with the coalition's widely respected guidelines. This combination of top-down standardization from bodies like the ISO and bottom-up advocacy from industry groups creates a powerful pincer movement, pushing the entire ecosystem toward greater interoperability. The ultimate goal of all this effort is a concept known as interoperability. In simple terms, this means ensuring that any servicing vehicle, any recycling station, or any other space-based infrastructure can successfully interact with any satellite, regardless of who built it or when it was launched. This is the key to scaling this technology from a series of one-off proprietary demonstrations into a robust, global, and truly functional market. Without interoperability, we risk creating a fragmented orbital environment with competing, incompatible systems. You might have an entire fleet of STRO-scale servicer vehicles that can only work with satellites built by their partners, while a NASA servicing module can only interact with its own designated clients. This would be wildly inefficient, incredibly costly, and would utterly fail to address the global nature of the space debris problem, which pays no heed to national borders or corporate branding. We can look to the history of other transformative technologies to see how powerful standardization truly is. The Universal Serial Bus, or USB, is a perfect analogy. Before USB, connecting peripherals to a computer was a nightmare of incompatible serial ports, parallel ports, and proprietary connectors. The development of a single, universal standard didn't limit creativity. It unleashed an explosion of innovation. It allowed countless companies to design mice, keyboards, external hard drives, and countless other devices with the confidence that they would work with any computer on the market. The same is true for Wi-Fi standards. A common protocol allows you to connect your laptop to a wireless network in a coffee shop in Tokyo just as easily as in your own home in London. These standards created massive, global markets by ensuring basic compatibility. The same principle must be applied to space. by agreeing on a standard physical docking interface, a universal spaceport, and a standard communication language for disassembly commands, we wouldn't be limiting what engineers can build. On the contrary, we would be freeing them to focus their creativity on higher-level challenges, like developing more advanced AI for autonomous decision-making or more efficient robotic tools, rather than wasting talent constantly reinventing the same basic connection hardware. Establishing these universal protocols is the essential, if unglamorous, groundwork that will determine whether our future in space is one of open collaboration and efficient sustainability, or one of fractured, wasteful incompatibility. Perhaps the most powerful testament to the promise of this technology is how it has already escaped the confines of engineering labs and boardrooms to capture the broader public imagination, transforming a complex technical challenge into a source of wonder and creative inspiration. For decades, the narrative of space in popular media has been dominated by two extremes: the pristine, hopeful exploration of shows like Star Trek and the chaotic, destructive battles of franchises like Star Wars. The concept of self-disassembling spacecraft introduces a compelling new third act, one of stewardship, adaptation, and intelligent renewal. We see this reflected in a new wave of science fiction literature, where authors are crafting stories not about fleets of indestructible warships, but about orbital mechanics and robotic surgeons performing delicate surgery on aging satellites. These narratives are powerful because they present a vision of the future that is not about conquest, but about caretaking, resonating with a growing public desire for sustainable solutions both on Earth and beyond it. This shift is also vividly apparent in visual media and art installations. Documentaries from major studios and independent filmmakers alike are increasingly turning their lenses toward the space debris problem, using stunning CGI and breathtaking footage from the International Space Station to make the invisible threat of orbital clutter viscerally real for audiences. These films do more than just inform; they inspire a sense of urgency and awe, translating the abstract concept of Kessler syndrome into a tangible story of planetary responsibility. Meanwhile, contemporary artists are incorporating themes of space sustainability into their work, creating sculptures that mimic modular satellites or interactive exhibits that allow gallery visitors to virtually pilot a robotic servicer, grappling with the same physics and dilemmas as real engineers. This artistic interpretation is crucial because it engages the public on an emotional level, transforming cold engineering data into a relatable human story about preserving our shared cosmic environment. The effort to demystify this technology extends far beyond the silver screen and the art gallery, finding a vibrant home in science centers and museums around the world. Institutions like the Smithsonian National Air and Space Museum and the California Science Center have developed dedicated exhibits on orbital debris and the new technologies being designed to solve it. These are not static displays of placards and models; they are immersive, hands-on experiences. Visitors can step into a simulator and attempt the delicate docking maneuver of a mission like Restore-L, feeling the tension of aligning with a spinning object using nothing but a robotic arm and a camera feed. They can interact with physical models of smart materials, touching alloys that change shape with heat or polymers that degrade under light, making the science tactile and understandable. This kind of engagement is invaluable for inspiring the next generation of scientists and engineers, showing them that the future of space isn't just about building bigger rockets, but about building smarter, more responsible machines. Perhaps the most democratic form of outreach is unfolding on social media platforms, where space agencies, private companies, and educators have become incredibly adept at breaking down complex ideas into engaging, shareable content. Animated explainers on YouTube visualize how a satellite might break apart along its smart seams. SpaceX launch webcasts dedicate segments to discussing how their newer Starlink satellites are designed for complete atmospheric demise. Engineers and orbital mechanics take to platforms like TikTok and Instagram to debunk myths, show behind-the-scenes testing, and explain why a particular piece of space news matters. This constant, accessible dialogue normalizes the conversation about space sustainability, bringing it into everyday life and ensuring that the public is informed and supportive of the billions of dollars and immense intellectual effort being directed toward this critical problem. The most impactful initiatives are those that transform passive observers into active participants. Citizen science projects, for instance, have opened a direct channel for the public to contribute to real research. Platforms like NASA Spot the Station app have evolved, with discussions now including how to visually identify and track some of the larger pieces of debris. More sophisticated programs allow amateur astronomers with modest telescopes to contribute tracking data on specific objects, adding valuable points to the models that predict orbital paths. For those less inclined to stargaze, there are online puzzle games like Debris Defender, where players use the principles of orbital mechanics to safely capture and deorbit virtual debris, their high scores contributing to research on efficient disposal trajectories. These projects foster a powerful sense of collective ownership and responsibility, making the preservation of space a participatory endeavor rather than a distant governmental mandate. This groundswell of public engagement is not a peripheral benefit. It is an absolute necessity for the long-term success of this technological revolution. Grand engineering projects require sustained political will and significant public funding, both of which are fueled by popular support. When people understand and feel connected to the mission of cleaning up space, they are more likely to advocate for the policies and investments that make it possible. This creates a virtuous cycle. Inspiring outreach leads to public support, which enables funding for more advanced technology, which in turn creates even more captivating stories and demonstrations to share. By inviting everyone to become a stakeholder in the future of space, we are building a foundation of societal backing that ensures these incredible advancements are not just technological triumphs, but a shared human achievement aimed at preserving the heavens for all future generations. As we bring our journey to a close, let's pause to reflect on the extraordinary transformation we've explored. We began with a stark vision of a cluttered orbital environment, a ticking time bomb of debris threatening our future in space. We've seen how this crisis has sparked nothing short of a revolution in spacecraft design, moving us from an era of monolithic, disposable machines to a new paradigm of intelligent, adaptable, and responsible systems. This isn't merely an incremental improvement, it's a fundamental rethinking of our relationship with the cosmos, one where every mission is planned with its end in mind from the very beginning. The implications of this shift are profound, touching on everything from immediate safety concerns to the long-term economic and exploratory ambitions of our species. The key takeaway is that this technology offers a powerful, multifaceted solution to our most pressing challenges. It directly tackles the urgent debris crisis by providing a controlled and safe method for end-of-life disposal, turning potential hazards into manageable events. It unlocks staggering new economic opportunities, transforming space from a graveyard of written-off capital into a dynamic marketplace of reusable and serviceable assets, saving billions and creating entirely new industries in orbital servicing and recycling. And perhaps most excitingly, it opens the door to previously unimaginable missions, from intelligent swarms that can reconfigure themselves for different tasks to deep space explorers that can dissect themselves to deploy a fleet of probes across a distant world. This is the true power of the concept. It doesn't just solve a problem. It creates a platform for a more ambitious, sustainable, and prosperous future beyond Earth. None of this would be possible without a breathtaking convergence of disciplines. The self-disassembling spacecraft is a masterpiece of interdisciplinary innovation, a singular object that blends the material science of smart alloys, the computational intelligence of advanced AI, the mechanical precision of robotics, and the foresight of international policy. It shows us that the grand challenges of our time cannot be solved in isolation. They require the collective genius of engineers, scientists, entrepreneurs, and lawmakers working in concert. This collaborative spirit, visible in partnerships between agencies like NASA and ESA and private companies around the globe, is what will ultimately ensure that these technologies are developed safely, ethically, and for the benefit of all humanity. It is crucial to remember that this is not science fiction. The foundations of this future are being laid right now in real time. Missions like Restore-L are already testing the robotic precision needed for in-space surgery, while companies like Astroscale are demonstrating the core technologies for rendezvous and capture in orbit. The materials, the software, and the prototypes exist. This is an active, accelerating field of development, moving from whiteboard concepts to flight-ready hardware at a remarkable pace. The revolution is already underway, happening in clean rooms, vacuum chambers, and control centers around the world. So, what does this all mean for us? It means that we are learning one of the most important lessons of our technological age. That true mastery is not just found in the ability to build and create, but in the wisdom to plan for an elegant and responsible conclusion. By learning to carefully take apart what we send into the heavens, we are taking a monumental step toward preserving the cosmos for the explorers, scientists, and dreamers of generations to come. We are transforming a problem of our own making into a profound opportunity, an opportunity to prove that we can be not just occupants of space, but its stewards. This story is still being written, and its next chapters will be shaped by the curious, the passionate, and the innovative. Stay engaged, follow the progress of these incredible missions, and who knows, perhaps you will be among those who contribute to building this cleaner, smarter, and more sustainable future among